Hello, sound is a phenomenon of local pressure variations and local particle displacements in a medium, fluid or solid. Typically we consider air. Last time we derived the wave equation to describe the derivatives of space and time according to the sound pressure. And now we will solve this wave equation, and what we will find is sound waves. In this slide we see the medium illustrating sound propagation, and in this case we see the pumping effect in this red box, the pressure variation according to time and space, and we see also the propagating effect. Let's see how we can calculate this. We start the calculation with considering plane waves, meaning that in y and z direction there is no change in the medium and only the x direction is of interest. Our Laplace operator contains terms according to the derivative of y and z. They are zero. In this case it is simplified to just one dimension considering the variable x. This is to be solved now. The general solution for this equation is given by the so-called D'Alembert principle, and the mathematicians tell us that any function f or any function g, which can be derived two times according to x and t, is capable of solving the wave equation. The only precondition is that the variable x and t are combined in the way x minus ct or x plus ct. That's all. The crucial part now is to understand the meaning of the function f of x minus ct, and we illustrate this by taking one example. The maximum of this function f of 0 is shown here. And in this case, the argument refers to the situation x minus ct is 0. So we can consider this as x at the point 0 and t at time 0. As time passes by an amount delta t, we have to insert this in the variable and find the proper x, which gives the situation again that f of 0 is found. Where is f of 0? This is found at a certain delta x, which exactly compensates the c times delta t, so that delta x minus c times delta t is again 0. We see this maximum now at that point, and in a plot according to the space, it is shifted by an amount of delta x. We do it again. We now find the maximum at 2 times delta x according to the time elapsed by 2 times delta t, and so on and so on. And if we plot that in another way, that now we have a second axis. On the y-axis we see the time, on the x-axis we see the space. We can follow the maxima and we can discuss at which time they are at which point in space. Okay, this is a very nice plot because we can see there's a certain slope involved with that, and the slope has an amount of delta x divided by delta t, and this slope is according to this internal structure of x minus ct exactly c. C is obviously the speed of this effect, which is a propagating effect of this function. Well, now we call it speed of sound. It was introduced as a factor for linearization of the adiabatic curve from thermodynamics. Now we find that's the speed of sound. That's something completely different. But it is also very interesting that the speed of sound is a thermodynamic constant, not more, not less. The speed of sound is most interesting for sound in air according to the temperature and pressure conditions which we have. And we can see on this slide that the speed of sound depends on the temperature. Actually, between 0 and 20 and 40 degrees there is a large difference. But generally the speed of sound is around 330, 340 meters per second. This is what everybody knows and remembers, maybe even from childhood, when you calculate in a thunderstorm the difference between the occurrence of lightning and the thunder. We can approximate the speed of sound for practical purposes very well by this equation, that it refers to the 0 centigrade speed of sound, 330 meters per second, plus about 0.6 centigrades added to that. Mostly we use 340, 343 meters per second for calculating the speed of sound in indoor situations, referring to about indoor temperatures. Now we focus on further examples of this general solution of the D'Alembert principle. It was given by the pressure as a function of space and time is any function, but the condition was x minus ct must be in the variable. We take now one example. It is called a harmonic wave. Harmonic wave means nothing but we use a sine or cosine function as the example for f. So we take the cosine, multiply with a certain factor, we call it pressure amplitude, and we take care that the variable has the form x minus ct. We also introduce a factor k and a minus, and we transfer this form into this form cosine in brackets omega times t minus k times x. This is just the formal introduction of a harmonic wave. We introduced k and omega as factors with the condition that omega equals to k times c. C was the speed of sound which we found before. The next is to interpret the meaning of those factors k and omega. We do this by considering this harmonic wave first in space, then in time. Let's start with a discussion in space. This means we are making a kind of photograph of the wave. We freeze the time at a certain time t0, so we get rid of the variable t and we just look at this function in space. This is plotted on the top figure, and what we will find is the cosine function, and the cosine function has a period of 360 degrees or 2 pi, as everybody knows. This period in space is called wavelength. We call it lambda wavelength. We measure it in meters. There's a problem in using the wavelength with the unit meters in the cosine. We cannot just put this wavelength in the cosine. This means we need a transfer of variables in space by using a factor which divides the period by the wavelength and introduces the inherent period of the cosine, 2 pi. The meaning is k is equal to 2 pi divided by lambda. It is nothing but a factor stretching the space variable. Now we don't make a photograph, but now we fix the space, the point in space, x, and we consider the development of this function according to time. This is even more logic to what acousticians do, because we put a microphone somewhere at a certain point in space, and now we record what comes in time, and we plot it. Again, we see a period. The cosine has a period of 2 pi again, but the real period depends on the frequency of sound, illustrated by the period t. What is the function of omega? It's nothing but the relation between t and 2 pi, and omega is used as a factor to the time scale, scaling the time in a proper way that the cosine makes periods of 2 pi, while a period of t in seconds is passed. So now we have learned the meaning of omega and k. Omega is the factor according to time, k is the factor according to space, and both are taking care of the fact that the real period in the cosine is 2 pi. Here we have the two factors again, and according to the relationship which we already know and introducing the frequency f, we can derive the well-known, maybe most well-known equation in acoustics, which determines the wavelength and the frequency together, and they are connected with the speed of sound. This is an equation you should remember by heart. This equation is best remembered by taking into account that the constant c is the product of the two variables, frequency and wavelength. In this little table we see some examples for very low frequency, 100 Hz, compared with the medium frequency, 1 kHz and 10 kHz. The associated wavelengths are 3.4 meters for low frequency sounds. I cannot show this, 3 meters is very wide. I can show 1 kHz. Everybody has 1 kHz as wavelengths in his or her body. It's like this. This is about 34 centimeters, so if you forget what is the wavelength at 1 kHz, just do this. And at 10 kilohertz we have about 3 centimeters, it's about that size. But now, considering from 3.4 meters to 3.4 centimeters, this is a very wide range of wavelengths involved. And this is one of the difficulties in acoustics, to deal with such big variations of wavelength. And the effects are basically taught in the next lecture, what happens when waves interact with objects, and here the wavelengths plays a very important role. Now, for convenience, we often use the complex notation of harmonic waves. In complex notation, we can take advantage of the fact that the exponential function is associated with sine and cosines together with the complex unit j. And we must consider, however, that in physics only the real part of this complex notation is noticeable. And this is illustrated by this video. Please only watch the red curve, which is the real part. So the x-axis is the real part axis. And as this complex vector is rotating according to the time or to the space, it depends on what we discuss in this moment, we can observe the cosine function as an illustration of the real part on the right side. After having solved the wave equation for plane waves, we now take the second example, which is in the same way as important as the plane wave. It's a spherical wave. So at first we need to consider spherical coordinates. Usually in a radius and a polar angle and an azimuth angle, we can describe the space in the same way as in Cartesian coordinates with x, y, z. And what is new in this consideration of spherical waves is that the sphere has a center. And obviously in the center there must be something which is called a sound source. Now, the wave equation is considered again with the Laplace operator and the right side, c square, and the second derivative to time. And with the consideration of no dependency in angles, which means the azimuth and the elevation angle have no contributions to the Laplace operator, we just have a simple equation according to the radius. This equation will lead to omnidirectional radiating sources, usually called a point source. A point source can be always considered when the actual source size is small compared with the wavelength. So even the human voice as a sound source or any loudspeaker as a sound source can be considered as a point if it is small compared with the wavelength. The mathematicians give us a solution in this case again. Again, it is a function f, and the content is very similar to the plane wave. R minus ct means previously x minus ct. It means a propagating wave into the positive r direction. But now there's a new information that we get also a factor 1 over r in the calculation of the resulting pressure. If we now introduce Q as the source quantity, source strength quantity, describing the volumetric flow rate in cubic meters per second, it can be shown by using one of the wave equations connecting the particle velocity and the pressure that the resulting sound pressure observed as a point r in space is dependent on a certain amplitude and a propagating factor. In this complex notation, it's the well-known factor e to the power of j omega t minus kr. This so far is the general solution for the spherical wave geometry, introducing the source strength Q as the volumetric flow rate in an harmonic solution. We now look into this solution a little more in detail. We can observe that the amplitude factor depends on 1 over r, which was introduced by the D'Alembert principle anyway for spherical geometry. But it's also interesting that it depends on omega, on the frequency. This means the more sound is radiated, the higher the frequency is. Finally, another important source quantity is the sound power, which can be also related to the sound intensity. So in the lower equation, we see that the intensity, usually it's the product of particle velocity and pressure, can be described very elegantly with the sound power associated with the spherical spread of 1 over r square And this is a number which can very well be related with the RMS, sound pressure squared, and the constants, density and speed of sound. We see in this illustration the spherical wave propagating from r equals to 0, where the sound source is, to the outside. The wave effect is very well illustrated. We also see the dependence of the amplitude with the propagating distance, illustrated by the 1 over r effect in the spherical wave. But there are very nice similarities with the plane waves, which is given by the propagating effect of the wave as such. And to summarize that, we now have learned the solutions in forms of plane waves and in forms of spherical waves. Both exist very often in practice. The spherical wave is usually found in a free space radiated by small sound sources compared with the wavelength. Plane waves do exist in practice very often as well. They exist in tubes, in ducts, in all waveguides, and so we already have learned a lot about sound.